Where we're going to talk about different sorting algorithms and how they interrelate with data structures. And we'll see that using data structures we've learned about in this class, we can improve algorithms that are out there. So I'll start by defining the sorting problem in a more rigorous way. I mean, you guys know what it means to sort, but you can make it more precise, and we'll want to, because it'll allow us to highlight some nice features of algorithms if we know exactly what we're doing. So a sort is a permutation of a sequence of elements that brings them into order according to a total order. Now, you guys have an intuition for what a total order is, but if you wanted to be really, really technical about it, you'd say it's total, in the sense that you could always compare two items and get an answer, yes or no. That's reflexive in the sense that you are less than or equal to yourself in our total ordering. And I'm using a modified less than or equals sign for our ordering. It's anti-symmetric, meaning that if x is less than or equal to y and y is less than or equal to x, these two items are equivalent, and it is transitive, in that if x is less than y and y is less than z, then x is less than z. And actually, if you look at the Java docs for how compare to works, they actually spell out that these are the properties that you need. So in Java, a total order is typically specified by compare to or our compare methods. And it's not, you can write a compare to that violates these, and I'll mention some cute examples of where this can cause you trouble, but ideally it has these properties. Now, one quick note is that it may not be consistent with equals. That is, the equals operation for strings, it's only true if the items are exactly equal semantically, but compared to if you're doing, for example, sorting by length, we would say that cat and dog are at the same level of the ordering. Okay? All right. So that's just a little bit of technical detail, but really the important part is this. This is what we're going to get. So now that we know that what we're seeking is an order according to some total order, I can tell you about inversions. So the sorting problem is given a sequence of elements. I want to reduce the number of inversions to zero. What's an inversion? Well, it's a pair of elements that are not in order. So for example, our 0 and 1, that's a pair. Are these in order? Yeah, that one's great. Okay, something that's not, well, 8 and 6. So 8 and 6, those are not in the correct order. So this is an inversion. It's no good. 8 and 5 is an inversion. 8 and 7 is an inversion. 6 and 5 is an inversion. 9 and 5 and 9 and 7. And those are the 6 inversions in this array out of 55 max. So when you look at this array and you say, yeah, it looks pretty sorted, but not sorted all the way, what you are talking about ultimately is the number of inversions. You have this sense, this is pretty good, right? And if I start putting the 9 at the front, that seems worse, just intuitively, and inversions captures that notion. And Gabriel Kramer from way back in the day, also, if you've heard of Kramer's rule, he's the guy who did that one. He also invented this concept. And then there's this guy, of course. Anyway, so the goal of sorting is given a sequence of elements with some number of inversions, we want to perform operations that reduce it to zero. So any questions about this space? Definition stuff here. All right. Scantilating. All right, great. So moving forwards, if we look at the algorithms, we're going to compare a bunch of algorithms for sorting. We have insertion sort, merge sort, heap sort, quick sort, others that we'll just take peeks at. We're going to characterize all these algorithms by two things. One is their time complexity. That is, how much time do they take? That's just the runtime, basically. Sometimes people use the word time complexity, so I'm going to use it today. And so, for example, depth first search had time complexity v plus e. If you make increasingly large graphs with ever more vertices and edges, the runtime is going to be theta v plus e. How about the characterizations of memory? How much memory does it use? We call that the space complexity sometimes. And so DFS has space complexity theta v for the call stack, for example. Now the graph, this is a quick point, it actually takes up more space. If you make an ever-increasing graph, it takes v plus e space to store all the vertices and edges, but we don't count that as part of the runtime of DFS because we're only thinking about the space that DFS uses. Okay, so just to be aware. Now today, we're not going to be talking about graphs at all. I've just given these as recent examples, but just to be aware, we're going to use the terms time complexity and space complexity for the runtime and the space for an algorithm, respectively. All right. So let's start off with an algorithm we've already seen called selection sort. So selection sort works like this. Okay, so this one's not going to be all that interesting, but the later ones will be cooler. All right, so sooner or later, blank. Oh, it's that movie. I changed that. Who did this? Okay, hold on a sec. That's spooky. I remember changing it. Google. Okay, here's all my links. How about this one? There we go. See, I remember it even had a 1.4 in it. Okay. Hackers. Hackers are making me look bad. Okay, cool. All right, so let's go to this demo that I wanted to play, not the old one. I'm a little scared of what other things might be old, but we'll find out. Okay, this is selection sort. So selection sort, you guys may remember, works like this. We have an array, and we want to find we want to get this thing into sorted order. And so the approach we took was find the smallest thing, and then once we know that, where should we put it? At the front. Okay, so we find the front thing, or the smallest thing. There it is. Put it at the front, and continue. Now I sort the rest. So what's the smallest item remaining? 15. Okay, so what should we do? Stay there. Good. Thank you, 15. Okay, what next? Smallest item? 17, let's say. So it doesn't really matter which 17 we pick. I think it's nice to choose the first one, but it would be correct to pick the other ones. So we have 17. Then what do we do? We swap it. All right, next up, 17. Okay. Now, one quick thing I want to note, just to remind you from the testing lecture, is that when we move it to the front, how do we move it? Swap. So I swap it. Why do I do that instead of just sliding them all over? Because that would be slower. Okay, so swapping is faster, and we don't really care about the order of the unsorted ones. Okay, so we keep this process up. 17's next, gets swapped. Boop, 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 boop. All right. Any questions about selection sort? All right. So we know that algorithm already, so we just raced through that one. And so we already discussed earlier that this is theta n squared time. We analyzed that during one of the asymptotics lectures. So the reason I bring this up is that algorithm seems inefficient. And the kind of the ugly thing about this algorithm is we kept looking through the whole array again and again and again and again to find the smallest thing. Like these items just kept getting scanned over and over. And so we could improve selection sort if only we had a better way of finding the smallest thing. Okay, so a natural data structure for keeping track of the smallest thing is a heap. Okay? And so what we could do is we could insert all of our items into a heap. I'm going to use a max heap. You could also use a min heap, but max heaps will end up being a little better for reasons that I think will become clear. So I'm going to take my array. I'm going to put everything in a max heap, throw away my original array, I don't care about it, and then create an output array, and just remove the max one by one and fill in the array from the back to the front, and I'll end up getting our items in sorted order. So let's try that out. Okay, clicking. Okay, this time, it's just not clicking for no reason. Okay. Saboteurs in our midst. Okay, so here's how heap sorting works. We have this array. Soon, okay? So I'm going to take all these items, and I'm going to put them in a max heap. Okay, so how do I do that? Well, to insert all my items into a max heap, we need an array. So I'm not going to go through every little detail here, but we create an array, and as you guys remember, the way we stored heaps, the tree representation 3, was we created an array with n plus 1 spots, and we leave the top one empty. Anybody remember why we left this empty? Because the math looks nicer when you want to compute your children and parents, and this is a common trick you'll see throughout the world. So just exposing you to it, even if it's a little silly. So then, and it also, I guess, makes your child and parent computation slightly faster, potentially. Anyway, so after inserting it all into a heap, which you guys hopefully know how to do, it's kind of one of those questions we might ask you on a midterm, we end up with an array like this. Now, is this thing in sorted order, this array? No, it's actually pretty terrible, right? I mean, like, this array, now the biggest item's at the front. That's exactly where the biggest item should not be. But have no fear. Now that we've built the heap, we can use this to do selection sort, okay? So if we do selection sort, in this case, where's the biggest item? At the top. That's the key. So we don't need to look through the whole array to figure out what the biggest item is. It's always going to be at the front. So what we'll do is we need to ultimately delete the 41. Now, quick question for you, because one of the important parts of our class is not just the algorithms, but also the runtimes. So I'd like you to think real quick, just for a minute, what is the runtime to actually do this step of taking the input and turning it into a heap? So I'll give you guys 20 seconds to formulate your thoughts. Okay, what do you think? Anybody want to wager a thought? N log n. So I'll call it big O n log n. All right, so that's a good answer. We'll talk about a better strategy than doing this in a little bit, but n log n is fine. All right. So then the next step is, all right, great, we got a heap. So now I want to produce an output. This is my output array. It's initially all zeros. When I remove 41, where should I put it? at the end of my array. Okay, great. There it is. So that 41 is sorted. All right. So after I've done this delete operation, you'll notice the heap does a bunch of funny stuff. So what ultimately happened is the 17 went up to the top, and then it sunk, okay, all the way down to the bottom. So we went from this array to this array by doing the normal heap delete operation you already know about. What's the runtime of that? Log n. Okay, good. So then now we want to delete 32. So where does that go? It goes at the end of the array after, well, I mean, not the very end, but the end, not counting the stuff that's already sorted. 26 is next. It ends up at the front. 19's next. It ends up at the front of the sorted spot. 17's at the next smallest, so it ends up at the front of the sorted spot, and so forth. So we just keep repeating this over and over until eventually our heap's empty, and we have here a sorted output. Now this array wasn't actually shrinking. I was just showing that for convenience. Okay. And I don't know why I decided there were 3 zeros at the end, but it did. All right. Any questions about this approach? Yes. Why did I choose a max heap? Good question. So a min heap, if we used a min heap instead, what would be different here? We'd fill in from the front. So it seems weird that I chose a max heap. Fair point. Okay, I'll show you why in a bit. So this would work exactly as well for a max heap versus a min heap. But when we do the next little trick, it won't work as well. Yeah. Why do I need to put it back into this output array? Well, I just want to say, it was to make it clear on the slide where the answer goes. You're right that I could actually just put it here, back in the same array maybe, right? Like we could be filling in the back end of our array, but I think it's more clear on the slide this way. So you have an optimization, which is you could use the same array. All right. Which, by the way, is the answer to that first question. Why use a max heap? All right. But let's see that in action, because that's... All right. That was a good wow. I don't know what the wow was for. You maybe saw the trick there. Okay. So before we talk... I, by the way, do not pick the words that yell key picks. They're random. So the first one... These are funny today. This one's suffer. Okay, it gets better, though. Like, by the time the third one happened, I, laughed involuntarily while I was at a meeting, because it happened. Anyway, all right. So, suffer. Okay, what I'd like you to do is figure out what's the total runtime of this version of heap sort, everything I just did. Okay, I'm going to spoil it. So the answer is n log n, and this is why. So you guys already did getting the items into the heap. That was n log n. That was the first problem you did earlier. Next was finding the largest item. Where's that? At the top. Theta 1. And then removing the largest item is log n, and putting an item in another array, which I didn't actually list on the slide, is also theta 1. So the overall runtime is n log n, or O n log n plus theta n. And why is this n here? This says 1. Why is this n? Because we do this n times. And then this right here, we do this n times. So overall, we could say it's big O n log n, and that is much better than selection sort. Okay? Way better. So by using a heap and kind of contorting what selection sort means, we're able to do it much faster. Now the memory usage, because we made 2 arrays, was theta n, because we have to make that second array. And while that's worse than selection sort, which used no extra memory, it was all in place, it's probably not a big deal. Maybe. It depends on your situation. If you have a huge amount of data, maybe you start caring, but often the factor of, just using n's not so crazy. So we're going to get rid of that memory cost in a moment, but any questions about this? Yeah. Yes. Oh, why did I say the word informally? Good question. Why did I say that? Seems pretty formal. I don't know. Informally. Okay. It's a double negative. I think it's because an older version of the slide maybe didn't use asymptotic notation. Okay, I'm going to add this, though. Is there some reason to say this? I don't think so. Okay. Good eye. Okay. Do we have any visitors, by the way? Potential Berkeley students who are just here for fun? Hi. Welcome. Oh, yeah. Hello. Oh, all right. Cool. Anyway. Any other questions? Yeah. Why do I use big O? I used this one because I know the answer is exactly theta n, because removing n items is going to take theta n time. Removing the largest item, it's possible that it doesn't actually take very much time at all. If, for example, all of the items are duplicates, then the sinks will fail, and this will just take constant time. Yep. So where I'm not sure, like these can vary. These are actually, this is like constant in the best case, log n in the worst case. So I call it big O log n. All right. Yeah. Selection sorts theta 1. Yeah. I don't think I said that out loud. Sorry. All right. So here's how we can save ourselves all that extra memory. So what we could do is, instead of using two different arrays, let's just use the same array. And what we'll do is treat the input array as a heap. Okay. So rather than inserting all of our items into an array of length n plus 1, we're going to do something called bottom-up heapification, which is a way to turn an array into a heap without using any extra memory. And I'll show you what that looks like. And then once you've done that, we can just proceed like we did before. So let's actually just see, there's this process right here. This is the original array. After we heapify in place, it's going to look like this. Now for this algorithm, because I don't want to use any extra memory, I'm not going to make a second array. And so let's see a little demo of what in-place heap sort looks like. And if you look at any real implementation of heap sort, which are kind of few and far between, because it's not actually that good of an algorithm for reasons I'll mention soon, it would use this trick. Okay? So what we're going to do is start by bottom-up heapifying the array. And so what that's going to look like is, this is a process I'm just throwing at you out of nowhere. Ordinarily, if we had an extra 10 minutes, I'd make you guys invent it with me, but I don't think it's that deep. So what we're going to do is sync the nodes in reverse level order. That is, we're going to start by syncing 17, then 41, 26, 19, 17, 2, 15, 32. And once we do that, then we will have a heap. So right now, you'll see this is not a max heap. What's an example of something that's wrong? The 2, right? That shouldn't be there. All right. So if we do this process of reverse level order sync, the resulting thing is a heap. So let's try it out. So syncing 17, what happens? Nothing. Syncing 17, nothing. Okay? 41, nothing. 26, nothing. 19, nothing happens. Okay. Now I hope you agree with me that these are all heaps, right? Little tiny heaps. All right, how about this one? If I sync 17, nothing. Okay? So that's a heap. All right, now 2. What happens if I sync 2? Okay, 41 takes over. So at that point, okay, funny story. All right. See how these are heap, 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 heap? There was a time 2 years ago when I made this slide. And I thought, I'm going to put the heap things really clear so everybody sees what's going on. And you'll see that the heaps get bigger. But actually here I'm just showing size 1 heaps. Okay. Last year, middle of the lecture, I realized, in spring of 2016, I never fixed that heap thing. Well, I'll fix it later. Okay, so now 2018 rolls around. It's 2 years later. And I have not made the graphic I wanted to. So maybe putting this here is not so useful. Anyway, high school student, don't come to Berkeley because it's just like 2 years of this. It's unacceptable. Anyway, all right. All right, now moving on. Okay, 15. We sync this number. Who takes over? 19. All right, good. All right, now comes 32. What? 41 takes over. Okay, so now at this point, we have a heap, and all of this useless garbage is there too, making us look bad for our visitor. Okay. So the point here, though, the punchline, ignoring this little heap thing, is since the tree here, the tree, if we think of this as the root, since it's a heap, the entire array is a heap. See, it says heap. God, embarrassing. But not as embarrassing as it was last year or the year before. Seriously, okay, let me tell you another story. This is the time in the semester where we were all in like death march mode, right? Like, it's intense. And like, I was like up a lot over the weekend working on bear maps. Because you decide, let's make a couple innocuous changes. And then they take like 15 hours to do. So anyway, I did fix some cool things in these slides. I felt pretty good about them. But I didn't bother rechecking my demo because I knew I'd fixed it. All right, anyway, let's move on. So the point here is, this is a heap. Look at it. Isn't it a beautiful heap? Verify it's a heap visually. We're good to go. All right. All right, so at that point, we've now bottom-up heapified. Is this sorted? No. It's actually maybe worse. It doesn't guarantee we fix any of our inversions, but nonetheless, at this point, now we can start deleting. Now this time, when I delete 41, what should I do? Put it at the end of the same array, and then use the other parts as a heap. So in effect, what I'm doing is the front part's a heap, and the back part is my sorted array. So I take 32. Now what? Goes here. All right, great. 27. Well, I'll let you guys try and figure. You know what? All right. Nah, you guys already know how to delete from a heap, so I'm going to keep moving because I think this question's maybe not that interesting because it's like a C-level midterm 2 question. All right. So when 27 gets deleted, where's it going to go? Go right there, and then all these numbers will move around. All right. What's going to change? Who's going to be the new temporary boss? 2, and then 2 will what? Sync. And so what you end up with is 2 over here. Okay. So I won't make you do the whole thing. All right, so from here on, the process is just exactly the same. Any questions? Yeah. What do you mean move the input? Oh, all this stuff gets moved. Yes, you're absolutely right. So every time I do one of these deletes, you'll notice that a bunch of array entries change, right? But the good news is that only a logarithmic number will change because what's going on, ultimately, is that 2 is moving to the top, sync, sync. So when you think about how this array moves around a lot, it's not going to change very much. So it involves a swap and then a logarithmic time delete. Maybe I should have made you do the problem, actually. Yeah. Oh, why did I bottom-up heapify the way I did? So the reason that I did the reverse level order sync is that approach is guaranteed to produce a heap. And this graphic was supposed to make it crystal clear, but does not. Now you could also, there are other approaches to heapify other than this one. This is just one that I arbitrarily threw at you. And actually, if you look at one of the old midterm problems from spring 2016, I have you consider 3 other potential processes and see which ones work and which ones don't. So there's actually like a whole not so interesting lecture, but I think interesting homework problem about different ways to heapify. All right, other questions? All right, cool. So that's a heap sort. And so now let's think a little bit about how this algorithm behaves. All right. So what I'd like you to do now is, again, fail. Okay, I didn't do it. But what is the runtime of this version of heap sort? It uses less memory, but at what cost maybe? Okay, so try and think about this. Okay. So, bottom-up heapification. Anybody come up with an answer for what you think the runtime of this is? N log n. So in the worst case, each sync takes O log n time, and there's n of those. So we could say it's n log n. So it's n log n plus n times 1 plus n log n, which is just n log n again. Now here is a tricky point. It turns out that bottom-up heapification process, while it is definitely big O of n log n, you can show, if you want, extra for experts, that it's actually theta n in the worst case. So while it is big O n log n, it's actually theta n, which is cool, right? I think that's really nice. And then more extra for experts, you can show that, it's not that hard from this point, but you can show that heap sort overall is theta n log n in the worst case. All right. So this is tricky. This theta n proof is a pretty fun one. So if you like those really hard asymptotics problems where it feels like it's going to be n log n, but it's actually n, this is the problem for you. Okay. All right. So moving on. What is the memory complexity of this version of heap sort? Okay, so it was suffer, then fail, then once. Okay, so it's like a flight inside joke for some of you to get. I couldn't believe it. All right. All right. So the correct answer actually kind of depends. I think it's constant. And the reason is you only need a constant amount of memory for your instance variables, for example, tracking size if you're actually to implement it. But you're not using any extra memory that, like, you don't have to make an extra array. So first thing, just to point out, the memory complexity of an algorithm does not include the data structure that already exists before your algorithm executes. That's unfair. So you don't count the array itself. So that was like the trick question there. Now, some of you might have thought it was log n because you think, well, probably you'll implement this recursively. And if you implement it recursively, then it's going to use log space for the stack. Fair point. Okay, so log n is a good answer too, but I like theta 1 just knowing, like, maybe I would implement it iteratively. But either of these is fine. All right, that's heap sort. Now you know about it. So heap sort, I think it's a cute algorithm. And later I'll show you some visualizations and you'll be like, yeah, heap sort's an especially cool character. But in the real world, it's very rarely used. And the reason is something called cache performance. Anybody in 61C right now? No? Oh yeah. How's it going? Wow, nice. It's a pretty hardcore double class. So anyway, in that class, you'll learn about caches. I can't tell you what they are right now, but basically it boils down to when your computer tries to get something from memory, it actually gets a bunch of things from memory all at once. And heap sort, because it jumps all over the place in your array, it's going to have bad performance compared to other sorts, but that does not change its asymptotic runtime. It just changes how long your machine takes to run the code. So it's constant factors, okay? So the worst case is n log n. It's constant space, but it has bad performance, and 61C you'll get a better appreciation for that, okay? All right, moving along. Let's talk about our old friend merge sort. So merge sort, actually any questions about heap sort before we go on? All right. Merge sort, our old friend. We already did this one during our asymptotics lecture, but let me remind you of what it is. Okay, so this is my demo of merge sort. And so it's a recursive algorithm by nature. It's like the traditional example of recursion. And so one way you could conceptualize merge sort is as follows. Okay, so this is what's called top-down merge sort. If you look in the optional Princeton textbook, they also discuss bottom-up merge sort, which is slightly different, but isn't meaningful enough for me to spend a lot of time with today. Okay. So top-down merge sorting looks like this. We have our array, and we split it into two roughly equal pieces. So in this case, I had 9 items, so it'll be red and blue. Okay. So then what we're going to do is we're going to merge sort each half. And so in that case, I have finished that, and I'm not showing the steps because this is a recursive algorithm. We're going to take the leap of faith that it actually worked. Okay. So after I merge sort these two pieces, then I need to merge them together. Okay, so how do I merge these? Well, I'm going to create an auxiliary array, and then I'm going to copy items, the smaller item from the two halves. Okay, so I got red and I got blue. So which one's smaller, 2 or 17? 2. So we'll copy 2 into my array, and we'll advance my I pointer. This is the traditional implementation for merge sort. Also, by the way, so I grew up playing Nintendo games, and these colors, it's like resonating with my soul because it reminds me, like, for example, this game Ikari Warriors. So hold on a second, let's go check this thing out. Ikari Warriors, YouTube. Okay. It's not that good of a game, but I remember playing it with my nephew because we were, like, close in age. Okay, it's like, okay, here we go. All right, look at this. Look at these two guys. It's like that cyan color and this pink color. And I cannot help when I see these Google Slides colors. Okay, this game is really tedious. Okay, look at that. Look. I mean, you can't tell me when you see the slides, you're not like, okay. If you spent like hours and hours and hours, anyway. Life vibrations. Okay, anyway, INJ. 15 and 17. Who's smaller? 15, good. Okay, so advance I. 17 and 17, which one's smaller? 17. I picked the left one just arbitrarily. 32 and 17, we'll take 17. So we keep advancing our pointers along. 26. Now we got 2 numbers left. What happens? 32. Okay, good. Now there's nothing left on the I side. We have to keep track of that somewhere. And so we'll just copy the remaining items, and now we've merged them. Okay, so we started with an array that was not merged. It was 2 sorted halves in those Ikari Warriors colors, and now we have the auxiliary array. Anybody ever play that game I just showed, by the way? All right, good. There's a code in that game. If you die, you can come back to life. It's ABBA. Don't forget that. All right. Anyway. Yeah. There was a bonus question for a final? Oh, it won't be the bonus question on the final, no. All right. I don't ever give the answer away. It's no fun. All right. Auxiliary array. We're done. Okay, any questions about merge sort? Okay. If we run out of time because I was showing a Nintendo game from when I was a kid, I will be sad, but all right, we'll deal with it. All right, time complexity. How long does that take to run? It's theta n log n. Why? See asymptotics lecture. How much space does it use? Theta n, because we made another array. Now, real merge sorts, like the one built into Java, actually do this array thing. They do it in a slightly funny way, where they constantly switch the role of the input array and the auxiliary array so they don't have to make new arrays. That's not really an important detail. But if you were someone who likes to hack things and get them really fast, there's like cute things you could do to make this code more performant, like creating two arrays and switching roles. But that's beyond the scope of our lecture. But we have this auxiliary array. Now, you might ask yourself, could we do something like we did with heap sort, where we play a trick? Now it doesn't use extra memory. And yes, you can. But what's interesting about in-place merge sort is that whereas merge sort is a beautiful algorithm, in-place merge sort is just a mess. It's horrible. So it's possible to do, but it's actually pretty hard to even understand what's happening, and the runtime is slow. Okay, so in real life, nobody uses in-place merge sort because it is well worth the memory to improve the performance and the simplicity of the implementation, mostly the implementation. Because when you build a library, actually it doesn't really matter how ugly or complex the code is if it's a library that just is well tested. Because there are things out there, even the Java quicksort's a little more complicated than the quicksort will do, but it's faster, and that's okay though, because, if there's one piece of code that 1 billion people are using, it's okay if it's complicated as long as it's the best it could be. All right. Anyway, but in this case, it is not worth saving the memory because you take a performance hit. Any questions about merge sort? All right. So we got selection sort, bad. We got heap sort, great, but slow. And then we got merge sort, which is great, but even better. Okay, so in principle, if you had to choose between these two, merge sort is the winner so far. Now let's talk about insertion sort. Okay, so insertion sort is the algorithm that if I hand you a set of cards and you try and sort them, it's roughly like what you maybe would do. Many of you guys have seen insertion sort somewhere. Somebody who has seen insertion sort before. Where'd you see it? YouTube. Someone else. Yeah. Okay. AP Computer Science. Yeah, got it. Okay. But some of you guys have not seen it, presumably. Or maybe you don't know it by name. And so how insertion sort works is that we start with an array, and this is going to be one version of insertion sort. This is, we start with an array, and then for every item that we see, we're going to put it in the appropriate place in the output. Okay, now that sounds lame, but we'll get there. So right now the output has nothing. And let's assume we're just building a list or something. I don't know what. So we take this input, and whenever we want to sort the number 32, we just stick it over there. Okay. Now, how about the number 15? What do we do? Well, in the output, we're going to say that goes to the left of 32. Okay, how about 2? It goes all the way to the left. Okay, how about 17? Where should it go? Between 15 and 32. So the algorithm, the reason it's kind of like what you do with a set of cards, is you're basically taking a card and saying, of all the ones I've sorted so far, where should it go? So this is not an in-place version, but I think it should be very clear what's happening. Okay. So here's 17. How about 19? Where should that go? Okay, so we scan through the array and we go between 17 and 32. There's 19. All right, 26. Okay, nope. All right, we'll put it there. 41 goes to the end. All right, 17, how about there? How about 17? Goes there. And I've just drawn the arrows there to say which order the 17s went in. It doesn't have to be this order, but it's a little nicer if it's this way for reasons that we'll discuss later. Now, this is not real data structures, right? This is just to give you a sense of what's going on. In a real implementation, you're not actually going to build a separate data structure, but hopefully it makes it very clear. So again, when I get to this point, really this is the key moment, right, is when 19 shows up, where should it go in the array? And if you understand the answer to that question, then you understand insertion sort. Okay. Yeah. The best case, okay, so going back, why was the best case runtime of heap sort theta n? If you have an array of all duplicates, it's just all the number 6. You can show that heapification is linear, deletion is linear, finding max is constant. Yeah. So all duplicates. Try it out later. All right, so that's insertion sort. And so you can do this in place using swapping. I'll do a little demo of this in a moment. But what I'll say is that for this naive approach, where if the output sequence contains k items, inserting a single item is going to take k time. So if we actually have another data structure and we have to put a number in and slide everything over, that could be slow. So let's see a more efficient way that uses swapping. So in this case, what we're going to do is we're going to use just a single array. So this turns out, okay, this could be a little confusing at first, but this is literally exactly the same as that really easy to understand version of insertion sort. So how this one works is, for each item, we're going to designate that item as the traveling item, and its job is to find its appropriate home, okay? And we're going to start with 32, and its job is to walk to the left until it can go left no further, okay? So I is the traveler, and J is, well, it's going to tell you the current spot of the traveler. So right now, 32 doesn't need to go anywhere. No. All right. How about, so at that point, we could say that 32, it's sorted, and all of these items are unexamined. Okay. Now the traveler is 15. Should it move? Yes. And it's going to travel left until it finds its home, which is right there. So I is where it is like the spot in the array where the traveler was, and J is where the traveler ended up. Okay. The new traveler is 2. Okay. So here, we're going to not move I. We're going to remember where I was. That's important. And then 2 is going to do what? Walk. Okay, so this is the part that feels like this should really feel like if you're sorting cards in your hand. Okay, so at this point, I'm going to make a quick note, which is whenever the 2 is moved here, we've temporarily broken our invariant, which is that all of the items to the left of the traveler's old home are sorted, right? This is not in sorted order, but we restore that invariant by continuing to walk. So at this point, once the traveler settles, the invariant, which is that the left side is sorted, is now true again. Now you might say, invariant, where'd that come from? Well, I didn't say it out loud, but this right here, saying that some part of the array is sorted, that's our invariant. So we have the sorted side, which should always be in sorted order. Okay, once a step is done. So now who's the new traveler? 17, and how do you know? It's I plus 1. That's why we kept I around, okay? So we get up to 17. How many steps is 17 going to take? 1. All right, at that point, this side's sorted. All right, 19, what's it going to do? Take 1 step. All right, 26, 1 step. All right, 41, it's just going to stay. All right, 17, what's it going to do? Take a bunch of steps, right? Travel. And the invariant is totally busted. We're all sad. Oh, wait, it's fixed. Good. All right. At this point, we have 1 item that's not sorted and a bunch of items that are. We repeat the process. We're done. All right. Any questions about insertion sort, the mechanics of it? Okay. So why do we need so many of these algorithms? Seems a little tedious. How many of these could we possibly do in a day? Well, no more today. But let's think about them because they all have their own interesting properties. And insertion sort has one property that I think is especially very cool. All right. So let's see a couple more examples. In order to do these examples, I need to, let's see. We're doing good. I'm going to delete that. All right. So in order to do, or to understand insertion sort's runtime, I'm going to show you a really neat trick. It's kind of like, remember we were doing runtimes and we had those little grids where we would color in triangles? It's going to feel a little bit like that. And so what we're going to do here is I'm going to take like the word potato. We're going to sort that word. Okay. Let's darken this room. And so now what I'm going to do is when P is the traveler, does P go anywhere? No. Okay, the traveler doesn't move. How about when O is the traveler? Well, I got to use my advanced English skills to go LMNOP. Okay, so it's earlier. So O is going to travel. So it's OP. There was 1 swap. How about T? Should it go anywhere? No. How about A? What's A going to do? Travel. So it'll take 3 swaps. How about T? No. How about O? It's going to do lots of swaps all the way up to the front. And so what I end up with is a diagram here showing who was the traveler, who got pushed out of the way by the traveler while the traveler was heading to their home, and overall, we can now have a picture of the number of swaps. So in this case, it was 7 swaps, and we can kind of see that visually a little bit. Okay? So the runtime is bad insofar as these elements are not gray. Here's another one. This is from the optional textbook. It's the word sort example. And here we can see that there are some letters that never moved. T, or didn't move when they were the traveler. So T didn't go anywhere when it was the traveler, though it did later get pushed aside by other letters. Right? Like, for example, when E traveled, E shoves everybody over. So E ends up at the front, everybody else is over. Okay, so that's a little inefficient, and that's why insertion sort's not going to be as good in most cases as merge sort or heap sort, because we end up moving everything over sometimes. But sometimes it's very fast, right? Like when X is the boss, what happens? Nothing. Okay, and so forth. And so when we get to this last step, for example, we have AELMOPRSTX, E. Well, E pushes its way to the front, basically, leaving these other, and there's 2 people already really still there. Okay, so in this case, there's 36 total swaps out of a possible somewhat more. All right, any questions about insertion sort? All right. So what's the runtime of insertion sort? We're back in positive territory. This time the word is sing, not like torture or something. Yeah. What's that? All right. So I think the best answer, okay, I deleted the answer slide. Let's fix it. All right, I think the best answer is that it is theta or omega n and a big O of n squared. I think that's the best answer. It's not the only answer, but let me tell you why this is the best answer first. Let me take this color away so it's the right thing. So it's big O of n squared, first of all, because in the worst case, this whole triangle is filled in. That would be n squared. That's visual, right? We see that. And the reason it's omega n is because in the best case, nobody moves, but we still have to look at every element of the array. So imagine it was A, B, C, D, E, F, G. We'd say, A, are you in the right place? A looks to their left and says, yeah, okay, I'm good. There's nobody over there. All right, B, you look over. Oh, A's there. Okay, I'm not going anywhere. All right, C looks over. All right, there's B. So in that sense, it takes linear time. However, you may recall... it's in the wrong font. We got to fix that. That's no good. All right, you may recall copy paste is not, now I got to fix the font again, is not best case. So technically, you could also say omega 1 if you were being pedantic, and that's fair. Okay. All right. So that's like not a super important point, but thank you for noting that. Sneaky. All right. All right, here's another question for you. This one's a little more interesting. So that was a just asymptotics problem. Now I have a really weird question for you. Say I have 1 million integers. I don't know where they came from, but I read them from a file, and I put them in an array. They're all sitting there in the array, and then I merge sort those numbers. So now they're all in sorted order, and I'm so happy that I have a merge sorted array. But then somebody comes along and changes just one of those numbers. They just say, I don't know, that one's 8 now. Now I want you to resort your array that has been corrupted by some evil entity, and I want you to tell me which algorithm would be best. And it's your decision about what best means. So you have to use one of the algorithms from class exactly as it was presented. You can't change it slightly. Oh, there we go. All right, hello. All right, answer. I think insertion sort's a pretty interesting one. Here I'm going to start kind of justifying what I'm thinking. All right. So let's think about we have an array which has some small number of inversions. Let's say Aylmoberx's, right? So I want to get this thing in order, and the problem is this letter B is in the wrong place. So this is kind of like the example we had here. We had an array that was pretty much sorted, and there's one bad item. Well, if I do insertion sort, it's just going to shove its way to the front, and if it has 5 inversions in this case, we're only going to do 5 swaps on the left. Now, actually, that property holds in general. For an array with n inversions, it takes n swaps to fix them. So, for example, this is an array which has 3 total inversions. There's an E, which is out of place, and an S, which is out of place. I mean, some of these other things are out of place too, but they're like the main culprits here. That basically E can shove its way to the front, and S can shove its way to the front, and ultimately we do n swaps for n inversions. Okay? Now let's suppose we did selection sort for this array. What would happen? Well, we would find the smallest thing, and that's A, and we keep it in place. We'd find B, and we'd swap B to the front. Well, now we have a bunch of other problems. That big long-distance swap has introduced more problems. So then we have to search and then put the E at the front again. And so selection sort is not going to be as good as insertion sort. How about merge sort? What's merge sort going to do? Well, it's going to cut the array in half and then sort each half and then yada, yada, yada. But ultimately, its runtime is going to be n log n. It's going to do a bunch of work. And then heap sort, well, heap sort's going to totally ruin everything and then fix it again. And that's also not going to be too good. Okay? So insertion sort turns out is the best answer. And in this case, you can actually calculate the runtime. So selection sort will be n squared in this case. Heap sort will be n log n. Merge sort will be n log n. And insertion sort will be theta n. Now, earlier we said in the worst case, insertion sort's theta n squared. But in the best case, it could be theta 1, actually. Or, sorry, best case, it could be theta n. Why can't insertion sort be theta 1? Because you still have to look and make sure everything's in place. Okay. So the overall runtime for insertion sort is n plus k, if you want. Instead of saying n squared, instead of saying omega n big O n squared, you could just say it's theta n plus k, where k is the number of inversions. Okay? So if k is very small, say 0, well, then the runtime is dominated by the checks to see if you're in place. And if k is very large, in that case, it will dominate n. So what we'll define, which I'm going to do now, stealing from Bob Sedgwick in the Optional Algorithms textbook, is we're going to define an almost sorted array as one in which the number of inversions is less than Cn for some C. So it's just linear number of inversions. In those cases, insertion sort is very good. Yes? It's n plus yn times k. So in this case, the runtime feels... So k is the number of inversions. The amount of work, I guess, is like all of these things. It's just time n for all these checks, and then k for this long one. That's why it feels n plus k to me. I don't know that you could say it's nk. I'm not sure if that's correct or not. But I think n plus k is a more clear case for it for me. Yeah. It's an interesting problem. What happens if you try to show that it's nk? I think it doesn't work, though. All right, one last thing I want to say, and then I'll wrap up, is that for small arrays, insertion sort's also good. So if you have an array that's almost sorted, which sometimes happens, like you have a database with a bunch of people, now you add a new person, and they're in an array for some reason, so you can just resort with insertion sort. But another example is if you have a small array, just 15 or so, then insertion sort is faster. Now that's not something you could prove. This is an empirical fact, not a theoretical one. And you could do a theoretical analysis like Donald Knuth would in his books, but we're not going to. But the rough idea behind this is that a divide and conquer algorithm like merge sort and quick sort, they're going to spend too much dividing and not enough time actually just getting straight to conquering. And actually, if you look at the Java implementation of merge sort, it does exactly this. And it's almost time. So if we look at this is the merge sort built into Java that arrays.sort uses, and it says if length is less than insertion sort.threshold, use insertion sort. So it's a real thing, and in their case, they use 7. Okay? So be aware that industrial sorts can be kind of ugly. So to summarize, we have 4 sorts of our day. We have selection sort, heap sort, and merge sort. Merge sort is the fastest of those so far, and insertion sort is best for these funny little cases, small n or almost sorted. So that's it. If you want an even weirder sort, that's like insertion sort plus, there's shell sort. But next lecture, we're going to pick up with my very favorite sort of all, which is quick sort. So I'll see you then. Hiya.